Alright, hi everyone. Just making sure that before you begin any kind of experiments, you have to wear your gloves on, safety glasses, and the safe lab coats on prior to any type of experiment you're going to do in lab. First of all, what we're going to do is to teach you guys how to polish a glassy carbon electrode. Here we have a standard glassy carbon electrode that is very dirty. I don't know if you guys can see it well, but it's very dirty. So first, what we're going to do is find some type of a container for you to put in the microcloth. And this is the microcloth that we purchased in the material group. Here, what I did was I found a beaker that's going to fit into the container that we chose. And what we're going to do is simply trace the mark on the carbon cloth and make sure that whatever we cut is going to be fitting into the petri dish, basically. So all we have to do now is to cut it and make sure that if you are using any type of shards, you have to be extra careful in performing those dangerous cutting sessions. Alright, so right now this is a not just any regular microcloth that you're going to see at a grocery stores. So this has to be specially purchased from whatever the vendor that we do. And luckily for us, they know how these will be used. That means they come with the back side that has a sticker already. So all you need to do is to just separate the sticker and place it on the petri dish. Nice and flat, just like this. Alrighty. Now what we're gonna do is to put the aluminum powder. So the one that I'm gonna use is 0.05 micron in size, but we do have 1 micrometer and 5 micrometer. So depending on how rigorously you need to clean the GCE, glassy carbon electrodes, you will go from the highest, the biggest size to the smallest size. And usually 0.05 is a standard one that we use. Be careful because these powders are very fine and they float everywhere. So if you make a mistake or sneeze into this bottle, you're not going to be happy about it. So we're going to take some and place it on to the carbon cloth. Sorry, not the carbon cloth, micro cloth. Okay, hold up. Okay, then next what we need is a squirt bottle of water. And we're gonna just put some water on top of it. Alrighty. So what you're gonna do is if you look at the glassy carbon electrodes, this is where we make an extra electrical contact to the potential set. So you want to avoid any damage to this part. So when you grab it, you're going to grab it like this and make sure the angle between the glassy carbon electrodes and the microcloth is 90 as you can. So you're going to hold it like this, put just on top of it very gently, don't push it too hard. And what you're going to do is you're going to make a figure 8. And you can already see that like there are some black stuff coming out. Probably God knows how long that has been there, but it is coming out. And the reason why we're making a figure 8 is to clean the surface from all degrees. So like if you try to do a circle, then you're only cleaning it to one side, right? So you want to make sure that you have all 360 degree of cleaning. I'm making a figure 8. And you continue this until you are done. So, hold up. What you can see is it was really dirty, but after just a couple times of polishing the electrodes, very clean. Very clean. So this is how you clean GCE. All right, so before you begin any type of electrochemical setup, you need three things. Your working electrode, which in this case is going to be glassy carbon electrodes, your counter electrode, which will be our platinum electrodes, and finally a reference electrode, which is saturated calomel electrode. All of our platinum electrodes are stored inside of a nitric acid bath, and it has to be stored inside. Just carefully remove the lid and fish out very carefully, because this is a nitric acid bath, of a single electrode, and put it into this is a water bath, so that we do not have any of nitric acid droplets getting everywhere. All right, so now here is an electrochemical setup. This is our saturated calomel electrode. Oh, here, this is our glassy carbon electrodes that we just polished and which is clean, and our counter. This black box over here is a potential stat. Simply, you will turn it on by pressing onto that power button, and all you're going to do is to make sure that the potential stat and the computer is connected, and you open up a software. So when you do open up a software, you have to make sure the software version is the same thing with the potential stat. And what you can do is you can go to the setup and do a hardware test to make sure that you are connected and everything is working fine with the potential stat. And everything is okay under the current hardware test, and we're good to go. So once we have this, what we're going to do is to actually physically set up this experiment. Here, we already pre-made a solution for this video. Typically, if you use a CH instruments for potential stat, you will have a color code where white is the reference, green is the working, and red is the counter. So because my glassy carbon electrode is the working, I'm going to make a connection and place it in to make sure that this is not touching the bottom of the beaker, which will limit certain type of reactions if you were to do that. Second, all right, so this is the platinum electrodes. I'm going to make sure that all the excess water was wiped out. And this is our counter. Therefore, it goes with the red alligator clip. And then it goes into the solution. So one thing we have to make sure is that this particular side of alligator clip that is attached to itself cannot touch the solution. So make sure whatever you put it in, make sure that it's only the platinum electrode that goes into the solution, and make whatever the adjustment you need to make sure your electrode goes in. All right, so a little bit of troubleshooting we have. All right, there we go. Nope, we don't have it. Welcome to the world of electrochemistry. Okay, we have it. Perfect. So now what we're going to do is to do the reference electrodes. What I'm going to do is I'm going to make sure that this gets wiped out. And I'm just going to dip it in water bath and take it out quickly. Because this guy is stored in a saturated potassium chloride solutions. Therefore, if you have too much of cells, sometimes that will interfere with your reactions. So make sure every contamination that you can avoid is avoided. And it's the same thing where it is placed without touching the bottom of the beaker. So now you can cut it. All right, so before you begin any type of experiment, you have to make sure that none of these three electrodes are touching. So the carbon electron is not touching any of the counter and the reference, and the reference is not touching the counter and the working. And it's the same thing for the counter electrodes. If they do touch, you short circuit, therefore there's no experiments to work on. All right, so we're going to move on to the actual computer setting. If this is the regular CH instrument software, here is the parameter and this is the technique. So first, we want to make sure that we know which potential window we're working in. So we'll do cyclic voltammetry. And then we need to set the cyclic voltammetry parameters, but we don't know what that is. So what we're going to do is we're going to set a big range of potential. So let's do negative 0.9 to 0.9. The low will be negative 0.9, where the final is going to be negative 0.9 as well to complete the cycle. It is going from negative 0.9 to 0.9, so that is a positive scan polarity. We will keep the scan rate fast, which is about 0.1 volts per second. Sweep segment means one segment means from here to the positive side, and the second segment will be the positive side to negative. So that makes a one cycle. Therefore, we're going to do at least 4 to make sure what we see is definitely real redox chemistry. And we're going to just have it at a really high sensitivity so we don't max out the current. So once everything is done, you click on this play button and it runs automatically for us. And you wait. It really looks like nothing is happening. Beautiful. So now the time has gone. This experiment is complete, and you can zoom in or zoom out however you want to manipulate the data. So at this point, it looks like nothing is happening, but if you click on this magical button where they show the exact data, they show this. This is a very interesting data where, wow. So from around positive 0.9 till about negative 0.3, there is a flat line. So what this is, so we call this a capacitive current. There's nothing going on, but then you see a sudden increase of the current, and you have this little peaks over here. So there's a little bump here, and there's another bump. And going back down over here, there's also another bump here, right? So what we're going to do is we're going to rescan this with a shifted potential starting around negative 0.2 to a little bit further down to make sure that we have whatever we have away from this window can be tested as well. So you go back to the parameter and you set the initial as negative 0.2, high, no actually, yeah. And then high is going to be negative 0.2, but the low scan will be, let's say, negative 1.6. And the final is going to be where we started. In this case, what I did was I switched the potential polarity, right? So I'm going from negative 0.2 to negative 1.6. So I'm switching the initial scan polarity to negative and keeping the rest of them same. And I'm going to click OK. And before I go on, CHI needs to be saved after each run. So I'm just going to save as, and whatever the data we save it here will be on saved properly and safely. All right, so once you have saved it, we are going to run the second one. All right, so the scan rate is done. Oh, sorry, scan is done. Everything is complete. So we're gonna open up the scan again. So here you can see that this is the first scan and this is the second scan, then reran. And starting about, let's say, negative 1 possibly 1.1, we do see a little bump over here. And we have another bump over here. So we're going to make sure that these bumps are considered within our electrochemical potential window that we're going to test. So usually what I do is about 400 millivolts from the peaks that are furthest left and the right. So here I see a peak around negative 0.6, so I will start from negative 0.2. But on the furthest right side, we have a peak around negative, let's say 1.0, so I will run it until negative 1.4. So that is going to be what I called my scan window. And I'm going to do is a slight change of my parameters. And I'm just going to increase the scan rate because scan segments, because I see that the first cycle was very different than the second one. So I want to make sure that whatever I see on the second one can be replicated to the third one. So I'm adding on a cycle number and running it. All right, so the scan is complete. So we're going to do the last check. And yes, indeed, we are able to see all the peaks that we have seen the previous one. And this first big scan is the first scan, but the second and the third one, I see that they're pretty similar. So I can take the last two cycles and make sure that is what we present. The electrochemical potential window is very important to figure out before you do any type of rigorous study, because if you were to stop the potential window around negative 0.9 and did not check anything below, then we would not have figured out there's another peak. So it is very important to have the widest window that you can think of and then slowly move it down towards what's actually needed for your system. Alright, so we have done what we consider a faster scan rate, around 0.1 volts per second. So if you want to change the scan rate, what you do is go to the parameters, and under parameters there is a scan rate function over here. So you can go to, let's say, 50 millivolts or 10 millivolts. Usually I do anywhere between 20 to 10 millivolts. So here, for the sake of this class, I'm going to do 0.05, which is 50 millivolts per second. So I just decrease the function of scan rate, which means I increase the experimental setup time. So now it is quite double the time that I need to wait for the CV to finish. Alright, so the scan is done. And here you see that you observed something very similar to what you have seen with 100 millivolts per second. But this scan rate dependent study is very important, where depending on what type of electron transfer mechanism or type of process you have, you might lose a peak, or the peaks could be shifted, or it could have a completely different shape depending on the scan rate. So it is quite important that you test out numerous scan rates before you can say this is what you see. Before you leave, you have to clean after yourselves. So first, it's quite easy. Make sure that all of the experiments are done, and you're gonna just remove it one by one. Off of the alligator clip. Make sure your waste of the chemical reaction you set up goes into the waste bucket. Your glassy carbon electrodes and saturated element electrodes will be washed. Glassy carbons must be cleaned before returning to where it was before, but SCE, so saturated element electrodes, will just go into its original container with the saturated potassium chloride solution in it. And the platinum electrodes, this is very important as platinums are very expensive. So you clean it with water, but do not wash them with ethanol. Please do not wash in ethanol. You simply wipe up the excess water and put it back to the nitric acid bath. And before you leave the station, please make sure the potentiostat is turned off by simply pushing that power button once more.